So our next speaker is our guest, Roman Garnett. Yeah, he's the professor at Washington University of St. Louis. This is a session on Bayesian optimization, and Bayesian optimization is one of the most commonly used methods for hyperparameter optimization. And Roman is currently at the forefront of this area, and he will tell us about his recent work on automated model selection.
Thank you. It's great to be here kicking off the Bayesian optimization block of the symposium. I wanted to talk about a project that was at NIPS last year about using Bayesian optimization for automating the process of model selection. But really, this project represents a stepping stone towards a larger vision that I want to elaborate on to motivate the work, and then I'm going to return to it at the end of the work, which is finding a fully automated pipeline for active learning. Active learning is a paradigm we've had in machine learning for quite a while now. The basic story is pretty simple. When data for your system is very expensive to obtain, for example, you need to get a human involved, like you need to ask a grad student to do something for you maybe, then we should be very selective and think very carefully about what data we obtain. And active learning, and I use this phrase pretty broadly to include similar ideas like Bayesian optimization, considers this task of obtaining the most useful data for your task as efficiently as possible. These types of problems where obtaining data is very expensive are pervasive. For example, in the natural sciences and engineering, obtaining new data may require, for example, running a costly laboratory experiment. But also right here in this community, hyperparameter optimization, or say architecture optimization for neural networks, represents an extremely expensive process that we should be thinking carefully about. It can take days to train a network, and I don't even want to think about the electricity bills. So active learning approaches tend to adopt a pipeline that looks something like this. We're going to have some small set of training data that we've obtained, perhaps at great cost. We're going to use that data to train a machine learning model. And then we're going to reason about a large space of unlabeled data that we could obtain or experiments that we could run in combination with this model that we've trained and whatever our goals happen to be, to select some queries to give to some kind of expensive oracle, like this grad student sitting at this desk. When we get data back from the system, we're going to incorporate it into our training data, and we're going to continue with this loop while resources allow. So I think this is a pretty simple idea for people in this community to understand, but I want to focus on one part of this pipeline, which is right here, where I said we're going to use some training data to train a machine learning model. And I want to ask the question, how would a non-expert in machine learning face that model selection problem? Say somebody from the sciences or engineering that wanted to use the tools that are coming out of this community to help automate their discovery pipelines. Well, they basically have three options. They can either become an expert in machine learning. They could begin by reading the 7,000-page proceedings from NIPS from this year. That's a daunting task for any of us. Another option would be to find a human expert in machine learning and convince them that their task is important and work alongside them to build kind of a custom model to make this active learning pipeline work. That's also difficult. I think many of us are at corporate parties a lot of the time, for example, so it's hard to make these relationships work. Instead, I think what's going to happen most often is that this non-expert's going to pick something off the shelf. They're going to use some model, say in scikit-learn or something. They're going to hope that the default parameters are good choices. They're going to cross their fingers and hope that it works for them. So if they're going to be using something off the shelf, the question I want to ask is, can we make something better that they can take off the shelf and use? Maybe something that's more automated or can be adaptive, and as we gather new data, can try to learn better models to explain the data that's coming out of this pipeline. So I'm going to propose a pretty simple procedure for helping to automate this kind of active learning loop, where instead of having a fixed model inside of that pipeline, we're going to have a dynamic bag of models that we're going to maintain throughout this process. Any one of these models could be a potential explanation of the data set. Then when we gather data, we're going to use all of these models. We're going to do something like model averaging, being aware of any uncertainty we may have in our choice of model. And then every time we get new data from this expensive pipeline, we're going to revisit the question of whether we want to change the bag of models that we're using. So we have this kind of automatically curated models. So we're going to switch between exploration in data space and exploration in model space. So we're going to try to do this in an end-to-end automated way. Bayesian optimization represents one instance of a type of setting where we want to be thinking in this way. And Bayesian optimization may itself be something we may want to automate in this way. And Bayesian optimization is basically an instantiation of this active learning idea for optimizing expensive to evaluate objective functions. Bayesian optimization has proven successful in many domains, including it's seen some work in terms of hyperparameter optimization. And Bayesian optimization has been quite successful when you can build an informative model of your objective function. In this case, Bayesian optimization can be extremely sample efficient in terms of its ability to optimize the function. And we're going to see some examples in the next talk of orders of magnitude speed up offered from Bayesian optimization over, say, random search. And the nice features of Bayesian optimization is that these expensive objectives, they can be non-convex. We can observe them without gradients. They can effectively be black boxes if they need to be. So if you have a problem and you're starting to check some of these boxes, then maybe Bayesian optimization might be something you want to consider. Bayesian optimization basically works exactly in this active learning loop that I showed on a previous slide. We're going to build a model for this objective function. It's usually a Gaussian process model, although other models like Bayesian neural nets, random forests have also been used in this context. Then once we've got this model built and maybe trained on some previous observations, we're going to use it to derive an optimization policy via, say, Bayesian decision theory, for example. So we're going to work out something like an expected utility that will be very cheap to evaluate. We can compute gradients, et cetera. And maximizing this surrogate expected utility is going to give us an optimization policy. And then the nice thing about many of the policies that have been proposed for Bayesian optimization is that they will automatically trade off between exploration and exploitation when considering this expensive optimization problem. Okay, so now I want to return to this question of trying to automate these active learning or Bayesian optimization procedures where we're going to be, as we gather new data, automatically exploring this space of potential models to explain our data set. And I'm just going to be looking at this one step right here. I'm going to imagine that we've got some data that we've already gathered, and we want to ask the question, can we automatically find a good model to explain this data? We need a space of models to search over. In this initial study, we focused on Gaussian process models. Gaussian processes are very useful for active learning, Bayesian optimization, in that they can represent, model very different types of structure in data, and they also represent uncertainty in a way that's amenable for developing policies. Gaussian processes are extremely flexible in terms of the structure that they can represent in data. Here's just an example of 16 different Gaussian process models for modeling even a one-dimensional function here. So each panel is just some samples from a Gaussian process model for this one-dimensional domain. And already right here, by changing the structure of the Gaussian process, we can represent many different types of structures in data. But the question we want to ask here is, if we've given a data set, so maybe just a few observations in this space, how can we figure out which of these models, or maybe which of an even larger class of models, is the best one to explain our data set? If we're going to be asking about, which one is the best, which explanation of the model is which model is the best explanation of the data, we need a way of kind of scoring how well a model explains a given data set. There's different ways of doing so. In the Bayesian formalism, we would usually adopt something called the model evidence. The model evidence is basically the probability that a given model generated your data set once you average over all of the parameters or hyperparameters of the model. And the nice thing about the model evidence is that you get this kind of automatic Occam's razor effect where more complex models are automatically penalized when you do this averaging over its parameters. So this model evidence represents a score that we basically want to maximize as a function of the model for our given data set. And that notion brings us to kind of a different way of thinking about this model search problem than normal. In fact, this is not really the Bayesian way of approaching model search. But I want to frame this question of automatically searching for a good model to explain a data set as an optimization problem. I'm going to imagine that we're going to have some space of potential models, in this case Gaussian process models, and we're going to think about globally optimizing this model evidence function over that space of models to find the best explanation for our given data set in that space. And the flexibility of Gaussian processes has led previous researchers to kind of build structured spaces of Gaussian process models that are amenable to kind of enumeration and search for searching over these different types of structures. Okay, so let's think a little bit about why this problem is a hard problem as I've laid it out. So we've got this optimization problem. But the function we're trying to optimize, this model evidence function, it's an extremely complicated function. The mapping from models to evidence is highly complex. It's extremely nonlinear. And one additional issue is that even kind of notionally similar models may offer vastly different explanations for a given data set. And an even further nuance that you don't necessarily think about all the time is that the similarity between two models in terms of explaining some data depends on the geometry of the data set itself. So just as an example, imagine we had a data set where we had a bunch of measurements that were just all extremely far away from each other, so just a bunch of isolated points. If this were the case, it could be that every model you might even consider positing as an explanation of the data might give you exactly the same explanation, that all of the outputs are just going to be generated independently. If that's the case, we don't even need to do model search. Whereas if maybe the data points get closer together, then the structure of the models might give you a different view of this evidence function. Another problem is that even estimating the model evidence for Gaussian processes is extremely expensive. So we can't compute it in closed form, and if we want to find an estimate, it's expensive. It's going to require something like cubic time work for the size of the data set we're reasoning about, and then even the constant factor in front of that cubic time is going to be pretty big. So we've got an expensive objective function. And another issue is that the space of models that we're going to be optimizing this function over is kind of naturally a discrete space. So we can't compute something like the gradients of the model evidence with respect to the model to help us optimize this objective function that we've set out to optimize. Right, so I hope you see where I'm going here. I'm basically building an argument for using Bayesian optimization. So we've got a nonlinear, gradient-free, expensive objective function we want to optimize. It's just like the perfect story for adopting Bayesian optimization. Okay, so that's what we're going to do. We're going to use the same scheme I showed you on a previous slide, but we're going to do it to try to maximize this model evidence function. So what we're going to do is we're going to build a model of this model evidence function. So we're going to build a model. It's starting to get a little meta. We're going to place a Gaussian process prior on this model evidence function, mapping models to their evidence. And then we're going to condition that Gaussian process on some models that we've evaluated, former posterior belief, and then use that posterior to develop a policy for optimizing that will trade off exploration versus exploitation in model space. Okay, but we're going to need to do something pretty weird here, which is that we want to build this Gaussian process prior for the model evidence function. Which means that we need to develop, say, a mean function and a kernel function for this Gaussian process that's going to take in models as arguments. It's kind of an exotic object that we need to construct. So for the mean function for this Gaussian process, we're just going to use a constant. We're going to rely on that Occam's razor effect in the model evidence. But what about the covariance? So we need to build this kernel that's going to take in two kernels as arguments. So we need a kernel. Again, we're getting kind of meta for the Meta Learning Symposium. And the job of this kernel is to look at the two kernels and examine the data set and determine a priori how correlated we think the model evidence will be if we measured it at these two different models. And so we had to scratch our heads for a while to think about how we're going to construct such a thing. And eventually what we decided was that we're going to say that two kernels are similar for a given data set if they offer similar explanations for a latent function at the measurement locations in that data set. So for a Gaussian process model at least, if you have one of these models, then it induces a prior belief for some latent function vector at the measurement locations. It's going to be something like an infinite mixture of Gaussian distributions. And then what we said was that if two models generated these two different prior distributions for these latent function evaluations, then we're going to say the two models are similar for this data set if these two prior distributions have a high overlap. If that's the case, then the two models are basically offering very similar explanations for this data set. And maybe we can expect that they have similar values from the model evidence. Whereas if the two models have very independent explanations for the data, then maybe the model evidence will be no longer correlated. I'm obviously skipping over quite a lot of details for how we're going to estimate this overlap, but we can turn this into a kernel. And just to show you in pictures, this is just a cartoon illustration of this kernel. We've got 4 kernels on the left here. Kind of 2 incorporate some periodic information, and 2 don't have that periodic structure. And then if you evaluate our kernel, you get this nice block diagonal structure like you might expect. We did some experiments in the paper, of course. I'm going to kind of breeze through them in the interest of time. But we compared this method for automating the search for a good model, which we call BOMS, Bayesian optimization and models for model selection, against a previously proposed greedy procedure. Everything was exactly the same, except how we're going to explore through the model space. So we tested on some one-dimensional kind of time series data, and basically it was neck and neck. There was no real speed up. But then when we looked at higher dimensional data sets where the model space was much more complex and much larger, then this ability to automatically trade off exploration versus exploitation in the optimization made dramatic differences. This is showing the log model evidence normalized by the size of the data. So this is actually like a 50 or 100 nat difference in the model evidence at termination. Okay, so we're able to rapidly and efficiently locate promising models for fixed data sets. And this exploration trade-off was really critical for leading to that speed up. Finally, I just want to quickly return to the overall vision that I laid out at the beginning of the talk, which was automating active learning. And these results for fixed data sets were promising, but I really wanted to show that we could use this in the inner loop of another procedure, active learning or Bayesian optimization, for example. So we're going to curate this dynamic bag of models by using this BOMS procedure to every once in a while select some new models for investigation. And we've done some initial work using this procedure to find a fully automated scheme for Bayesian optimization. And we compared our procedure with an off-the-shelf model what a non-expert might use today, and also a static bag of models that can represent uncertainty in model space but doesn't do any active exploration. So we're using Bayesian optimization for automating Bayesian optimization. Again, it's pretty meta. This is the last slide. So the initial results look pretty good. This is a really small table. This is just a small slice of the real table, which looks like this. But the takeaway messages are that the methods that can represent uncertainty and the choice of model tend to do better. And then also our procedure, which uses this BOMS procedure to automatically, dynamically curate this bag of models, seems to work the best. So this is one step in the direction of this overall vision of finding this fully automated pipeline for active learning / Bayesian optimization. I think there's quite a lot of work to still be done, but I thank you for your time, and I'll take any questions.
So no question. Everything is well understood.
I think Bayesian optimization is no longer cool, I think. Due to some recent blog posts, perhaps. But anyway, thank you for your time.